So I'll just now talk about signal conditioning, alright, where we are gonna talk about the ADC, from analog to digital conversion. Alright, it's because for signal conditioning, right, your V-in, the conditioning problem comes about is, I think, is that the V-in, alright, your officially analog signal, for example, your analog signal is, this is 1 volt, alright, you have a certain analog signal of this thing, okay. Well, when you come to your ADC converter, your reference may be talking about taking range from maybe 10 volt to 20 volt. So you're only sampling from 10 volt to 20 volt. You're not sampling anything lower than that. Alright, so that's why I think, okay. So therefore, that's why I say that an ADC has an input range which is generally defined by its low reference voltage VSS, often zeros, and a high reference voltage VDD or V reference. So to ensure that the analog signal V-in lies within the input range of the ADC VSS and VREF, which is, this is VSS, this is V reference, okay. So it must be scaled. So the analog signal must be scaled, or amplitude of the analog signal must be reduced, or the analog must be amplified. Alright, so you're going to amplify your analog from 1 volt to a certain larger voltage, so that it fits within this range, so that you can sample your stuff, things like that. That's what I think lah. It's not an exact explanation, but at least something that you kind of can visualize that the sample can, because if you didn't do some amplifications or reduce, it may actually lies within here, so you can't actually compare. So you want to bring it upwards so that it can actually be seen in your reference frame, so that you can sample it lah, yeah. So therefore, once we do this, then how can we sample? How does the system sample? So the system actually sample using the successive approximation technique. Alright, so how this works is that say your VSS is equals to 0, your VDD is equals to the highest. So your particular V-in frequency is already within your VDD and VSS already. Alright, so it's within your range to sample. So in order to sample, alright, this is your analog V-in voltage. Right, so yeah, so this is your analog V-in voltage. Alright, so what they do is that at the first bit, alright, 0 1 1 0, alright, is the output. Why let me see. Okay, I think this is better. I'll just use this to explain. If it happen that your V-in, alright, is lie within VSS is equals to 0, sorry, which is at this point, alright, which is VSS equals to 0 to VDD, correct? Then if happens is lie within your V-in already, you need to know whether is your V-in, where you want to locate where's your V-in, right? Because now it's within this range. How can we know that which part does this V-in belongs to? Alright, so if you take in a 4-bit system, the first bit will actually determine whether is your V-in lower than your half VDD or not. Alright, so the first bit will talk about half VDD. Alright, while the second bit will talk about 1/4 VDD, and then 3/8 VDD, etc. Alright, but anyway, I'll just continue first so at least you get the meaning of that. So at first, it will determine whether is it lower than half VDD. If it's lower, then it's 0 bit. Alright, if it's higher, then it's 1 bit. You get what I mean? So currently, our V-in is lower than half VDD. Alright, so we can say that this is 0 bit. Alright, so the next step, what we do, the next time step is, not time step but rather the next step of what we're gonna do is to compare the 1/4 range. Alright, so compare 1/4 VDD. Alright, so you'll ask whether does your V-in, alright, larger than your 1/4 VDD or lower than your 1/4 VDD. Alright, if it's higher, alright, then it's feedback to 1. Alright, so from here you can actually set up a range to actually somewhat small. As you can see, your V-in is really the range to, how do I say, the range to capture your V-in is getting smaller and smaller, so you're approaching your V-in already. Alright, So the next thing that they are trying to do now, then next they actually compare with a 3.8 VDD. Alright, so this line over here is a 3.8 VDD. Alright, you may wonder how does this value comes about. I think you just take it lah. I think it's a standard way of doing the steps. Alright, so they actually narrow down to 3.8 VDD. So is it higher than 3.8 VDD or smaller than 3.8 VDD? So from here you can see that your V in is actually higher than your 3.8 VDD. So over here you just write as 1. Okay, and the last one is that you compare with 7/16 VDD. Alright, 7/16 VDD. So if you just take a look, this is actually 8/16. Half is actually 8/16. Okay, so if you take a look, this is actually 6. 3/8 is actually 6/16. Alright, so it's trying to give you the range between 7/16 and 6/16. Alright, you see, so 1/4 is actually 4/16. Alright, so as you can see, it's so you take 8/16 and 4/16, and then you slowly decrease. The 8 over here you decrease by 7, over here the 4 you increase by towards the 6. But anyway, this is the values that they also plug in one. So they just say that whether is it higher or lower than 7/16. So therefore it is lower, then it's 0. So most likely you know that your V in is in between 7/16 VDD and 6/16 VDD. Alright, so this is how you approximate your V in through successive steps. So first step you do this, successively you do this, successively you do this, the next step successively you do this. Alright, so you slowly locate where's your V in. Alright, so this is how they actually do this method lah. Okay. Smaller or bigger, so everything you need to know is that if your V in is whether is your V in higher than lower than your requirements. For this case, 3/8 VDD, is your V in higher or lower? If your V in is higher, you just output 1. If it's lower, you output 0. Alright, so normally you will need to compare whether is it higher or lower. Higher, then if it's higher, then 1. If it's lower, then 0. Please take note of this thing. Alright, so this is the approximation method. Alright, and it's a successive approximation technique for 4-bit ADC. It's a 4-bit, so that's why you can see it's 0, 1, 1, 0. Alright, so 4-bit, this means that you have 16 possible intervals of resolution. Alright, so over here you can straight away define your V in as in between 7/16 and 3/8, where 3/8 is actually 6/16. Alright, so I hope you kind of get what I mean already. I would suggest you may want to also read these. Alright, the first value, alright, the first one over here, this one is your most significant bit. This one over here is your least significant bit. Alright, because this is 2 to the power of 3, this is 2 to the power of 0. Alright, so you straight away know that which is most significant and which is the least significant. Alright, and then you may want to check whether is it a bottom half of a half top, or is it the top half of the. So bottom half is this one. So now what we're doing is the bottom half, right? So I think you get what I mean. Alright, and you slowly narrow down by a quarter, so you can find your next bit, your next significant bit. Alright, and so you keep on half of the range until you reach what you want. Alright, although this is not a bit, not of the half, but I think you get what I mean. Alright, so you slowly do lah. So what I have been saying, this is actually a one method of approximating your V in signal. Okay, while there is also other successive approximations, or you can use a network of precision resistors or capacitor. I don't know what the hell, but you use resistors or capacitor to help you predict the same thing that what we are doing. Alright, you can also use an analog comparator. Alright, and you can use the sample or whole process to actually do things with it. I'm not go into details, you go and read it up if you're free, and then you can do a next series of stuff that you want if you're free. Alright, so just the summary is that each of the step you requires 2 clock cycles. Alright, so 1 to change the reference voltage and 1 to make the comparison. So over here you requires two clock cycles, so I think you will want to understand. Alright, it's just one of it. One of the clock is to change the reference voltage, one is to make the comparison. Or if you were to head back all the way in this, alright, so this one over here is to your reference signal. Alright, so your ADC over here is doing the job. Alright, so ADC uses the successive approximation, comparing your V in to your V reference. But before that, you need to also filter off or signal condition your signal such that is. So over here, I think you'll condition the noise also. So after you clean your V in, then you can finally process your V in with relevance to your V reference. Alright, and then after that you can do what you want. Alright, so this is the thing. Alright, so one clock is to change the reference voltage, which we have say is a reference signal. Alright, while another bit is to compare between your reference signal and your V in over here. Okay, so I hope this is pretty clear. And then so the clock cycles means that one of the bit, alright, 16 ADC clock cycle in all 8-bit ADC. Alright, so I think a bit different. So 8-bit uses 16 clock cycles. Alright, I don't know, for you to think about it. So also that it is always cheaper to buy a microcontroller that contains an ADC rather than your own self go and buy another ADC by yourself. Alright, because most of the microcontrollers should contain ADC in it. Alright, but sometimes having a separate ADC is a better choice. Alright, if you need to convert an analog signal, alright, close to the signal source. Alright, I think if you want a better accuracy, you can actually use a separate ADC. I don't know what he's trying to say. Analog signal and then signal source. Then where's my signal source? Is it V reference or what? Leave you to think about it. And then multiple channel ADCs are usually implemented by multiplexing the input to a single ADC unit. So instead of having one V reference, you may also have multiple V reference. Alright, tapping into the analog digital converter, I think. Okay, so yeah, so therefore this is the same thing, nothing changed. Alright, analog to digital. Yeah, it's the same thing that we have said just now. But nonetheless, you may have a multi-value V reference. So you may have a series of V reference to do. Alright, things like that. Alright, and this is the general stuff. Take note that this successive approximation method, alright, help you to produce one bit by one bit. Alright, as you can see, at each of the thing you compare. Alright, between half VDD or 1/4 VDD, alright, you're gonna require a 0. You're gonna generate a 1 bit by 1 bit stuff. Alright, so each of this thing is a 2 cycles, I think. I don't know, I forget already, but something lah. Is it 2 cycles? Yeah lor, so each step requires 2 clock cycles. So one to change the reference voltage. Alright, so you change the reference voltage to the 1. So you change, at first it's VDD to VSS, and then now you change to half VDD compared to with VSS, and then next you compare half VDD with 1/4 VDD. So you keep on changing your reference signal to converge into your particular signal that you want to look at. Alright, so this is telling you that you convert analog to digital, and from digital you can convert back to analog. That's all. Okay, and then yeah, over at this page it will tell you that the ADC module SAM3X8E is purely an ADC module. Alright, its purpose is to convert. It's a pure ADC. It is not a microcontroller. Alright, so it by itself it can have 10 or 12 bit resolution, 1 megahertz conversion rate to actually help you to convert to convert from analog to digital. Alright, and you have 16 channels to convert all of the V reference all together at once. Alright, and then the rest you go and own self settle. Alright, and then you can look at the data sheet. Alright, the data sheet over here, and yeah lor. So over here he says that you can also ADC within the Arduino Dual is there is a 12 ADC channel. So this is talking about microcontroller having ADC. Alright, previously the the SAM system is only a pure ADC, it's not a microcontroller, so be careful of that lah. Okay, and then the default resolution is 10 bit, so it's 2 to the power of 10, but you can also change it to 12 bits, alright, 2 to the power of 12, alright, which is 4096 level, alright, where you can own self go and type analog read resolution in your Arduino, where the resolution you can type 4096, I think, alright, or 1024, depends on what resolution you want to look at, alright. And the reference signal from Arduino is standard, is a 3.3 volt, alright. So an external reference voltage can be used through AREF pin in your Arduino, alright, but requires removal of resistors from the PCB, alright, from your PCB board, or if you have any resistors lah, alright. But nonetheless, if you want a reference voltage, you require to use a AREF pin to connect to your Arduino. Okay, so this is something. So over here, if you want to code, you initialize your analog pin, alright, is equals to pin 3. So pin 3 is actually a analog pin, I think. So after that, you initialize the value of the analog pin to be equals to 0. So the analog is by default there's no analog signal, right? So it's therefore equals to 0 lah. Alright. Then you in the setup, you set up as serial.begin 9600 because it's a bulk rate. Alright, it's the speed that you want the Arduino to process. Alright, and the void loop. So within the loop itself, you set that the value is equals to analog read. So you read your particular pin, alright, and then you serial.print9 your thing. You read your analog. Alright, so it's just simply that. So you just plug in, you just set your analog pin as equals to pin 3, and then after that you can straight away read already. Alright, so it's just that. Alright, but so therefore I don't think you'll need to connect to the AREF pin if required. Alright, or the AREF pin I think is the 3 volt. Alright, I mean the pin 3. Alright, so let's see where it goes. In your Arduino, the AREF I think is not the pin. Alright, that's not I say is your pin 3. No, okay, your AREF is actually by itself, AREF. So you want to connect a reference signal into here, okay, with a certain resistors if you need. Alright, but just now he say no resistor, right? An external reference voltage can be used through AREF but requires removal of resistors from the PCB. Alright, but you can also connect to resistors, I think, because from internet I actually see that they are connecting with resistors, you see. So you see there is some resistors going on. Alright, I'll leave you to think about it, but anyway, this is your reference signal. So you can actually set your pin 3 as a analog pin. So you can set any of your pin as analog pin. Alright, and there's a digital pulse width module, so you can also you can also generate a motor. Okay, you can also program a motor using Arduino Uno, you still remember, because the motor can use pulse width to run your stuff. Alright, so yeah, come to think about it, it's pretty nice already. Yeah. So if you want to have a digital to analog, then I think you can put it over here. Alright, so the digital Arduino will actually send analog signal to the motor, I think. I don't know. Okay, so this is something that you may want to know also lah. Okay, so I think this is it for the signal processing, yeah, signal conditioning. Alright, so you can condition your analog signal and things like that. Alright, so I'll leave you to think about it, but just remember the codes over here. Alright, initialize your value is equal to 0. Be very careful. Alright, and then after that you want to loop, put it in the loop, so you keep on taking analog readings from your analog pin. Alright, so this code over here is telling you that you're taking, when you keep on taking in analog signal from an analog pin. Alright, and therefore after you take in already, you print your whatever analog values, so that yeah, you can see your analog system lah. But is it if it's temperature, then temperature, if it's the distance, then it's distance, things like that. Okay, so this is it for this whole lesson 8. Alright, and I'll do the lecture 9 later. See you there.